Hello everybody, Math Hobo here, and today we will be discussing one of my favorite proofs in all of mathematics. And the reason that this proof is one of my favorites is that it utilizes so many different areas of mathematics and combines them into a specific proof. So let's get right to it. This is a proof of the area of a circle, and we'll be using some geometric intuition in this proof. We will be inscribing regular polygons inside of our circle, and we will see how, as we take the area function of those polygons and take the limit of the sides tending to infinity, then we will perfectly approximate the area of this circle. So now what that means is if I take a triangle and inscribe it within our circle, and because it's a regular polygon, this triangle will be equilateral. And if I take the area of this triangle versus the area of a square inscribed within our circle, the square will better approximate the area of the circle as a whole than the triangle does. And the pentagon will better approximate the area of the circle than the square does. And the hexagon will better approximate the area of the circle than the pentagon does, and so on and so forth. So we can see that as we take, let's say that we have n sides to a polygon, then as we take the limit n tending to infinity of the area function of the polygon, that's poly sub n, which means that a polygon which has n sides. So as we take the limit of n tending to infinity of the area function of a regular polygon with n sides, we get the area of circle. And this is what I will demonstrate to you today. So let's begin by describing exactly what the area function of a polygon n is. So because we have n sides, and because 6 is a very easy number, we will begin with the hexagon. So n is equal to 6. Now let's do something here. Let's triangulate this polygon. So we divide it up we divide this regular hexagon up into triangles, and each of these triangles will be congruent, and they will all be equilateral triangles because, and we'll discuss that later. So if we would like to start with this, because it's a regular polygon, the sum of the interior angles of our polygon, so the sum if you add up all the interior angles, is going to equal 180, or actually let's stick to radians in this proof. So pi into n minus 2. Yes. So pi into n minus 2 is the formula for the sum of the interior angles, and if we wanted to calculate one of these angles here, then let's call that alpha. Alpha is equal to pi into n minus 2 divided by n. That's because if you take the sum of the interior angles and divide it by the number of interior angles, then you get the degree of, or the radian of one interior angle. So the angle that we would like to be talking about is the angle that the triangle makes. So this angle is just alpha divided by 2. So alpha divided by 2 is equal to pi into n minus 2 divided by 2n. And just to simplify things, we will rewrite alpha divided by 2 as phi. So our angle here will be phi. And what we are trying to do ultimately is to calculate the area of this polygon here. So we will drop a perpendicular from the center of our polygon to the base of the triangle. So that is our perpendicular, and we will be using that because we know the area of a triangle is half base times height, so we will try to codify exactly what the base and the height are. So if we have angle phi here, and we know that since our polygon is inscribed within a circle, this length from the center to the edge of the circle here will be the radius r. So that is what we are given. So then the height of the circle, h, the height of the triangle, h, will be equal to the radius times the sine of the angle phi. So r sine phi. And the base here, which is what we will try to multiply with h to calculate the area of the triangle, base will be equal to 2r cosine phi. And the reason that it's 2r cosine phi is because r cosine phi is just this length here, and 2r cosine phi will be this entire base. So now we have written down the closed forms for the height of the triangle and the base of the triangle, and now we can discuss the area of a single triangle, which will be half base times height, which will be equal to half times r sine theta, r sine phi, times r 2r cosine phi. Let me erase the extraneous things. Yes, so, and this half and the 2 cancel out, and the r's multiply to become r squared, and we have our area of a single triangle is equal to r squared sine phi cosine phi. And if we would like to calculate the area of the entire polygon, then all we must do is take the area of one triangle and multiply it by the number of triangles that tile the polygon. Well, let's ask ourselves, how many triangles exist? Well, 1, 2, 3, 4, 5, 6, the exact same number of sides that exist. So, and the number of sides is n, so all we do is multiply by n, and we get is equal, so area is equal to area polygon with n sides is equal to n times r squared times sine phi cos phi. And now what we would like to do is we would, as we discussed earlier, take the limit of n tending to infinity. Because as we create a polygon with more and more sides, it will better approximate the area of the circle. So let's take the limit as n tends to infinity of the area function of a polygon with n sides, of a regular polygon inscribed in a circle with n sides, and that is equal to the limit as n tends to infinity of nr squared sine phi cos phi. And now let's erase our picture so we get some more space. And let's rewrite phi. So we have the limit n tends to infinity of nr squared sine, and since we would like to rewrite phi, well, what is phi? Well, if you remember, in one triangle of the, in one triangle, the internal angle was defined as phi, so the 2 times that interior angle will be the entire interior angle of the entire polygon, which is alpha. And if you remember, we determined alpha to be equal to pi into n minus 2 divided by n. And that's because the sum of the interior angles is pi into n minus 2, and we divide that by n to get a single interior angle. So that implies then that phi must be equal to pi into n minus 2 divided by 2n. So that is the expression for phi, and let's plug that in to our limit here. So sine phi, so that's sine pi into n minus 2 divided by 2n times cosine of pi into n minus 2 divided by 2n. And that is our limit. And what we will do now is we will show that this entire expression is equal to the area of a circle with radius r. So let's begin. We can simplify this product of sines and cosines because it's sine phi cos phi, or sine phi cos phi. We can rewrite it as half sine 2 phi. So we can rewrite it as half sine of pi into n minus 2 divided by n. And that is the simplified form of this here. So then we multiply by nr squared, and we get the limit n tending to infinity of nr squared divided by 2 multiplied by sine of pi into n minus 2 divided by n. Now this seems like a complex limit to evaluate because we have one n here, we have another n here, and we have another n inside the product here, inside the sine function as well. So what we must do is we must use L'Hopital's rule. So if you recall L'Hopital's rule, it is that the limit of well, we can use n in this case, n tending to a of f of a by g of a in certain cases where the limit is indeterminate can be rewritten as of f prime of a, or sorry, the limit n tending to a of f prime of n, this should be n as well, limit of f prime of n divided by g prime of n, where the primes denote the derivatives of the functions. So we can use this, but well, how do we use this? We don't have a clear quotient here. So what we will do is, because we have this coefficient here, nr squared divided by 2, we will simply divide this by 2 divided by nr squared. And those two things will be equivalent. So then we have this limit over here. So then we have f of n as this function, and g of n as that function. So let's take the derivatives of each of these functions. Well, the derivative of this is going to be equal to cosine of pi, well, let's simplify the inner expression here. That's simply pi n minus 2 pi divided by n, which is also equal to pi minus 2 pi divided by n. So pi minus 2 pi over n. So cosine of pi minus 2 pi over n multiplied by the derivative of the inner function, which is simply, well, let's differentiate this. The pi cancels out because it's a constant, and we get negative 2 pi ln of n, or natural log of n, whatever you prefer. And let's now differentiate the bottom function. The bottom function will be equal to, well, the derivative of the bottom function will be equal to 2 divided by r squared into the natural log of n. Wonderful. So we have come up with a easier limit to evaluate, and we still have our limit n tending to infinity. And now we can cross off certain terms and evaluate. So the natural logs of n cancel out, the 2's cancel out, and what we are left with is negative pi divided by, divided by r squared. It's divided twice, so it's equivalent to multiplying it. So negative pi r squared cosine pi minus 2 pi divided by n, and limit of this entire expression n tending to infinity. And, well, what is this equal when n tends to infinity? Well, n is only found once in this entire expression, and it's found at the denominator. And what happens when you have a fraction in which the denominator tends to infinity? Well, the fraction simply equals 0. So here we get cosine of pi. And we all know that cosine of pi is equal to -1. So this entire limit evaluates to -1 times negative pi r squared, which simply is equal to pi r squared, which is the area of a circle. Thank you very much.